Good afternoon, everybody. Thanks for joining today's seminars by NCCAV Center. The past seminars have been already uploaded to the websites, and the upcoming seminars will do the same thing as well. And these seminars that you can see are on a monthly basis by NCCAV, and these seminars are part of a larger seminars that we have on a weekly basis. So if you are interested in receiving information about the weekly seminars, please email Stacy or Fanta and to be included in the calls for weekly seminars. But these seminars that you can see here are seminars by NCCAV, and I would like to thank the sponsors of the project and CDUT Center who enabled the research of this project, as well as other sponsors of the project, Downtown Greensboro, Verizon, and RTI. With that, for today's speaker, today's talk is on data-centric architecture, the foundation to CAV design and performance. And we are lucky to have Mr. Bob Leigh to be the speaker for today. He has been developing new markets and building technology companies for over 15 years as an engineer and technology leader. Bob graduated from Queen's University with a degree in mathematics and engineering, and has used in his education in control and communication systems to develop and build a solution for a variety of industrial solutions in engineering, manufacturing, and transportation. Bob has a spanning career in small companies and has been the founder of two. In his recent position, he has been serving as the director of market developments for commercial markets at RTI. And I'm not going to go through all the bio. You can see the flyer for the detailed information. I would take this opportunity to invite him and for today's talk, and the stage is yours. Let me stop my sharing.
Great, thank you for that introduction. I'm just going to start sharing my screen as well. So thanks for having me on this call today to present our perspective on autonomy and data-centric architectures and really the revolution that's going on in many different markets, frankly. But today we'll focus on autonomous vehicles and connected vehicles. So I've got a presentation is not too long, hopefully not the full hour that we had allocated, and happy to answer questions as we go along and leave some time at the end as well. So if it's all right with everyone, I'll just get started. Assume you can see the presentation clearly. So I'd like to first talk about a little bit about RTI, give you some background on who we are, why we're here talking about this today, and the automotive revolution that's underway right now, and specifically designing for level 4 and 5 autonomy, and then our experience and perspective on autonomy in general, and how a data-centric design can help you be more innovative and competitive and build better solutions for these different autonomy applications. And then we'll have just a brief example of how no specific customers, unfortunately, because most of the work that our customers are doing is very secretive, but an example of the architectures that are being built by our customers to herald in this new evolution or revolution in autonomy. First, to start with RTI, we like to say that we live at the intersection of artificial intelligence and pervasive networking, two very important and hot technologies topics recently, both AI and different types of autonomy as we try and build more intelligence into many of our systems, but also the advance in networking, 5G being part of that. And really these two things are going to be a revolution in the amount of information and what we can do with that information going forward. And you really do need both. You need the smarts within the machine, but you also need access to data. And these two things combined give us access to a lot more potential for innovation and new applications. And when we say we live at the intersection, we're a software company that really connects these things together, connects the data to the applications, connects applications to each other in these very distributed networks. And you can really think of the future transportation system as a huge global distributed network where you have many mobile parts of that network, the vehicles, and then other static parts of that network being anything from roadside sensors and compute functions at the edge to back-end databases and systems. And all of this connected together really can transform our transportation system. So we're the #1 software framework for smart machines and real-world systems. We're in a lot of systems that you may or may not get exposed to on a daily basis. A lot with the U.S. Navy and other parts of the U.S. Department of Defense, working with medical imaging systems, air transport systems, in hospital robotic systems, as well as connected devices. Large-scale energy systems like the Grand Coulee Dam and offshore wind systems, and then autonomous vehicles as well, which is one of our fastest-growing markets. So what all these things have in common is they have some very hard real-time requirements in terms of their performance, how fast they need to react to the world, but they're also cyber-physical systems in that they're real systems that operate in the real world, and they have a distributed architecture of some type, and they're trying to make the system run better, whether that's through autonomy or access to more data or what have you. So our expertise is really bringing the infrastructure to these autonomy systems, and we're involved in many different consortia, from AUTOSAR to the Industrial Internet Consortium to things like ROS and the Autonomous Vehicle Computing Consortium, really trying to advance the state of the art in thinking about how we build architectures for these types of systems. So let's talk a little bit about the automotive revolution. I'm sure you're all familiar with many parts of this, but I'd like to share our perspective as well, so we have some context for the rest of the discussion. If you think about technology disruptions, they often don't happen, and you don't notice them until all of a sudden they're here. And these pictures are illustrative of the first motor vehicle that was on Fifth Avenue in New York City, and 13 years later, there's one horse and carriage, and really the mode of transportation completely flipped. So when we think about autonomous vehicles, it's very much likely to be like this, where we probably passed that one vehicle that's of something close to resembling level 4 autonomy on the road with all the testing and prototyping we see out there. But as soon as that becomes commercially available and commercially viable, very likely that within a decade it's going to be the dominant form of transportation in some way. Although I think that's very hard to predict exactly when that is and what it will look like. And automotive is a great example of a slow, gradual move towards autonomy that is all of a sudden accelerating. And I think that acceleration is because we're moving into a software-centric world. So start off trying to improve upon the physical structure, the body, the power plant within the vehicle, move to more sophisticated engines, and each phase gets shorter and shorter as innovation accelerates, until we get to the 1980s, where we have electronics, which really are providing the basis for the vehicles we see today, and the innovation that we're building now, software, which needs that electronic architecture and platform before we can properly implement software solutions. So I'd say the phase we're in now, let's just pick a date of 2020 into the future, is really about the innovation of the software within the vehicle, and how we make that software, how that software changes how we interact with the vehicle, how the vehicle behaves, and really how the entire ecosystem of transportation can evolve and change. Now, if we break that down a little bit further, what we're seeing within the vehicle is a change from the signal-based electronics architecture of the past to something that's more software-based, and more centralized. So as I'm sure you know, there are hundreds of different ECUs all doing a different specific and very purpose-built task within the vehicle. And if we want to build a smart, intelligent, autonomous system, that architecture just won't work. There's too many different decisions being made all at different points in the vehicle, many of them redundant and making the same decisions with different code in different parts of the vehicle. So what we're moving to right now is this domain architecture where we can centralize in different domains within the vehicle certain aspects of the architecture. So you might have a domain controller for the chassis, for example, and all of those functions, and a domain controller for the steering and the braking, and centralize some of those functions, or at least coordinate those functions within that domain. And then as we evolve into the future, what the industry is looking at is something called redundant zonal architecture, where different zones that now can cross between the different boundaries that are traditionally built for a vehicle, things like chassis and powertrain and body, and have different zones based on functionality and have redundancy built into those systems. And then as we get into high levels of autonomy, level 4 and 5, we're looking at centralized architectures. We have a central brain that's running the entire vehicle based on some very high performance compute systems that probably aren't even available yet today, but you can see in the trunk of the car where that looks like a massive server running all the artificial intelligence systems within that vehicle. So this is clearly a software world that we're moving to, and the big names in the industry agree with that. The manufacturers that are the most innovative and planning for the future are trying to reorient their decision making, their organization, even their supply chains around having software expertise as opposed to the electronic and hardware expertise that they need today. And as we move to electric vehicles, this is even more important because it's actually much easier to build an electric vehicle than a traditional ICE vehicle, and there is more software required and more dependency on software. So we see this move to software, and it's not just about how do I build a better vehicle that can go faster and be autonomous. Really, once we have this perspective of software within the vehicle, it can then expand to many different parts of the transportation experience, things like diagnostic services and car sharing and different options for infotainment within the vehicle, and even getting into monitoring driver health and offering insurance and connected IoT services for doing everything from vehicle maintenance diagnostic to improving your neural net for the autonomous driving of that particular vehicle. And the list goes on and on. I'm sure there's things that we haven't even thought of. So as the manufacturers and the OEMs are looking to the future and they're looking at this software-based future, it's not just about how do I build a better vehicle, but how do I provide more capability to the consumer, both the person buying the car as well as all different parts of the ecosystem. And that's disrupting the business model, that's creating more opportunities for different ways to make money, and also opening the door for more competition, as we see with all these startups that are now competing with the traditional OEM, traditional manufacturers. But it's not just about the vehicle, it's also about the infrastructure and how that vehicle interacts. Everything from the V2V, so vehicles communicating with each other to make the roads safer, to communicating with infrastructure to be able to better manage road conditions and traffic and our public spaces, to communicating with individuals, pedestrians that are on the road, again, making it safer for them, as well as communicating to the back end and be able to collect this immense amount of data that our vehicles will have as really huge sensor nodes out there roaming around in the world, gathering tons of data that we can take advantage of and managing that. So if you're software company or a manufacturer or a university doing research or anyone in this ecosystem, how do you build your software? How do you build IP? How do you design your architecture so it can handle all this change that's coming in the future? Because that's the one thing that we know for sure is it's going to be unpredictable. We don't know what business models will win out. We don't know what ecosystems, whether it's AUTOSAR, coming from the traditional OEM and built originally in Germany, or ROS as the robotic operating system, something that's newer for the automotive space. Which one will become dominant? Which hardware platforms will become dominant? How do I build an architecture for a level 2 or a level 3 vehicle today, but also plan for the future where I need more sensors and more capability and build level 4 or level 5? We're really seeing it move away from building software essentially from scratch every 5 or 6 years when you have a refresh on your vehicle, to building architectures that need to last for 5 or 10 years and evolve and adapt to new requirements and new capabilities that you have to build into them. And that's a huge challenge. When you're building software, that is a huge challenge. It is very hard to build software today that's going to not be a liability down the road because there's features that was never designed for. But fortunately, there is a solution to that, and the solution is a data-centric design. And we have experience with these types of designs for the last 15 years, building and deploying them and helping our customers maintain them. So what do I mean about data centricity, and why do we want it? Well, I think everybody's familiar with data centricity, even if you don't know about it in this context, because you probably work with one in a database, either directly or indirectly. And in the IT world, especially enterprise systems, no one builds an application that isn't based around a database. Because when you need to share massive amounts of data between different applications and different users, the database is really the only way to control how to access that system and easily scale sharing that information. And a database essentially is a data-centric system for static data or historic data that really doesn't change. But what we need here is a data-centric system for data that does change. Data in motion is what we call it. Data that you want to consume in real time. And that is a much harder challenge because of the cyber physical constraints that the real world puts on our applications. You can't wait for a minute to retrieve the data that got logged to a database before you make a decision about whether you should break or not. You need to have that data and make that decision within milliseconds, if not microseconds. So when we look at data centricity in the context of autonomous vehicles, we can look at building perception and planning systems, and it can greatly improve developer efficiency, improving performance, managing complex data, and allow you to leverage IP across many different systems and platforms with an adaptable framework. If we look at these software-defined architectures of the future, then by having a data-centric architecture, you really can out-innovate the competition because you build the system around the data, which is really the value in your architecture, and the value in your applications comes from the data. So by putting the data at the core of the entire architecture allows you to innovate and do new and different things with that data, unlocking the potential of that data as you move into the future. And then when we think about teleoperations, which is an important part of a level 4 and level 5 autonomous future, is the ability to connect and remotely manage and control these vehicles. Really, we've never done this before in a public setting and on scale. So innovation and adaptation to a changing landscape is going to be key to be competitive and to come up with the right solutions. And having access to a lot of data from many different sources will really enable that innovation and that competitiveness. So let's break down the architecture a little bit more and look at what does it mean to be data-centric. So first, let's start with the way most embedded systems are built. At least this is the way they start out. You have a bunch of applications running on a bunch of different nodes, and you need to connect them together. So you may pick a technology that's probably message-centric, so you have to package it into a message and send that message out to another node. And so what happens is you need to build your application logic. That's what you really care about. That's the core IP that you're building for the system. But you also have to worry about discovering all those other nodes. Is it static? Are they always there, or do some of them come and go? You have to worry about reliability. What's the reliability of my network, of my hardware? What about boot up times? What about, you know, if one goes offline and comes back online, what do I do in those situations? So you have to write code for that. You have to worry about encryption and authentication. Sometimes you can get away with just using transport level encryption authentication, but it's not very granular, so you may have to layer on top of that or augment that with some additional capability. And then there's all these other things like message filtering and quality of service, like how reliable do I need to have that data that you have to worry about. So instead of focusing on writing your application logic, in most messaging technologies, what you end up doing is spending a lot of time writing lower level code that really should be part of the infrastructure and ensure that your data gets where it needs to be on time and reliably. Now, you've built the system, it works great. You've spent all this time figuring everything out, but what happens if you add a new node? Well, in a message-centric system, if you add a new node, now you have to worry about all these things all over again because the new node maybe introduces more uncertainty. It has to be tuned. You have to do updates to the API interfaces to access that new node, and it can be quite a mess. When we look at sort of a further evolution of that, usually, especially in an enterprise system, we move to a centralized broker approach, which really means a server somewhere managing all the communication. So this makes it a little easier to add in new nodes because there's a standard for how you interface. So you're simplifying things like message filtering and caching and addressing and discovery. That all becomes easier, but you're actually making it more complicated to manage latency and throughput and scalability. You now have a single source of failure, and if that goes down, how do you fail over? So you add some complexity there. So the data-centric approach is to essentially create infrastructure that manages data and manages data for all these different applications. And the critical thing as an application developer is the infrastructure, and in our case, it's RTI Connects DDS, our product that implements the Databus, manages all of these different things like message filtering and addressing and quality of service and encryption and authentication, and you only have to worry about your application logic. And because this is a quite mature technology and architecture, it has the capability to layer on additional domains where you have different actors, you know, isolated from each other. You know, one might be a safety critical domain, another one might be for high performance data communication in a perception and planning application. And this becomes a very, very powerful architecture where each of your publisher subscribers, as we call them, or each application only really worries about the data that it needs to share with everybody else. It doesn't have to send messages. It doesn't have to format them. It doesn't have to worry about addressing. It doesn't have to worry about how the data is going to get there. It just publishes the data into this infrastructure, and then someone else, whoever needs it, is going to receive that data, and becomes very simple at the application level. Now, there's a lot of complexity within the infrastructure to make that happen, especially when you consider all this is done without servers and brokers. So it's still all peer-to-peer, making it very fast and very scalable. So as your system evolves, what we're really doing when we move to a data-centric architecture is changing from a system that looks like this in a message-based, where you've got lots of interconnections between them. You have to worry about addressing. You have to worry about APIs. You have to worry about how the message is formatted, and essentially becomes more and more complex the more nodes that you add, the more applications you add, to an architecture that looks like this, where every application defines its interface around the data that it has and the data that it needs, and it's defined in a standard way and controlled by the infrastructure. And as you add more nodes, it scales very well. You don't have added complexity based on the number of new nodes that you're adding to the system. So now I'd like to delve a little bit into the standard, DDS. It stands for Data Distribution Service. And it is really the standard for implementing this data-centric architecture, or what we call a data bus. So it's managed by the OMG. It's a very mature standard. It's been around for many, many years. There are a number of different implementations and competitors building DDS implementations. RTI is the largest, and usually the leader in developing new standards and evolving the standard to add more capability. The other thing that's unique about DDS as a communication standard is it defines both the API layer as well as the wire protocol layer. So if you're using the standard and conforming to the standard, any vendor can be interoperable at the wire level as well as interchangeable at the API level. And for us, this is very important to have an open ecosystem where we have something that's very healthy in terms of competition, but also we have a way to ensure compatibility with this standard. And then DDS is also a foundational standard to other standards or pseudo standards. As I mentioned earlier, we work with a lot of industry consortia. Many of them define their own standards or their own industry norms or de facto standards within the industry for using for communicating between vendors and suppliers, or for managing a supply chain, or if it's within the U.S. military for their programs. And many of them use DDS as the foundational connectivity standard for these larger industry standards. And most recently, over the last few years, AUTOSAR Adaptive includes DDS as one of the connectivity standards that they support. And then the new version of the robotic operating system, ROS2, also is based on DDS as the standard for communication. So what does it really mean to have a DDS-based architecture and a DDS-based system? How does the data actually get exchanged? And this is a question we get right away from anybody who's experienced building embedded systems, because we're just so used to thinking in messages or signals, or we're used to thinking in central brokers and data and servers with a database essentially that controls how all this information is shared. And DDS has neither of these. But what they do define is a shared global data space. And this shared global data space is essentially it's entirely virtual. It's defined ahead of time usually, and it defines what data and the type of data that's going to be shared. And this is key, because if you want to have access to all the data everywhere, you can't actually have access to all the data everywhere. But what you can have is an understanding of what all the data is and where it might be, and that's defined in this global shared data space. And then you can get that data when you need it, or really the infrastructure provides your application with the data that you want when you need it. So this shared global data space is like a table in a database, in that it's defining things like what are the names of the different values, what type of data it is. We organize it in topics instead of tables. We call them topics. And then we have different applications that will either publish or subscribe to these topics. And so this is a very powerful architecture in that we're defining this interface for every application that's using it, but then the applications only need to define and access the parts of that shared global data space that they care about. And then the infrastructure will make sure that they publish that data that they have to publish and get the data that they need to publish. And we can do all this very quickly because it's peer-to-peer, as long as we have the right understanding of everything that's out there, which is again built into the infrastructure. So when you think about your architecture, it's not just about the connectivity. That's the core piece of it. And so the connectivity is defined by DDS. But then there's all the other pieces that make your system run well. And when we're working with our customers, usually they're very distributed, different applications running on different nodes, sometimes even on different networks that need to be bridged. And the communication is the core, but on top of that, we can build things like visualization and debugging tools, and recording and playback tools, and prototyping tools. And this data-centric architecture is really powerful for doing that, in that you can add on all kinds of tools that have access to the data, manipulate just the data, but provide a lot of insight into what all of the different applications are doing. And with these tools, you don't ever have to like build hooks into the application themselves, because we're just accessing the same data that everybody else is accessing on the databus. This data-centric architecture is something that can continue to evolve. We have this concept called the layered databus, where you can split out the different essentially functional and performance domains within your architecture into different domains, essentially, that have different performance characteristics, different type of data needed, and stack them on top of each other or stack them against each other. So if we think about the transportation ecosystem, you have the in-vehicle domain, where you actually may have a safety domain and another domain for infotainment or other systems, and they can be separated within the vehicle, but then they can also be connected to other data buses that are outside the vehicle, perhaps collecting a different subset of all of that data to understand where the vehicles are and how fast they're going, and how then they can calculate how dense the roads are and what the conditions of the weather conditions or conditions of the road are, and that can then share data with a larger data bus that's perhaps doing traffic management, or a municipal government maybe collecting information from the roadside systems to see, when do I need to plan for maintenance, and all that can be connected to even to the cloud. And so with a data-centric architecture and with DDS, you can actually take data from anywhere in this layered data bus and share it with any other application on any other node, any other domain, and you can do this fairly easily. So this is where the power of data leads to innovation and more applications and rapid response to competition or new requirements, because you have this really rich and deep access to data within your network. I want to bring this back to something I mentioned earlier in the automotive space, where they are really moving from a highly distributed ECU architecture to a central zonal architecture. With the traditional systems that we have today, you essentially have to rewrite your code if you're going to move it to a different platform, especially if that platform is fundamentally different. But if you're building with a data-centric design, and you're building with DDS, and you're building with RTI, then your application code becomes entirely agnostic to the underlying hardware and network that you may need to use. So you can really move those applications from an ECU to a domain controller, to a central GPU, and even up to the cloud, so that you can offload systems for capability from the car entirely, especially if you have a 5G connection that's fast enough to stream all of your infotainment, even the GUI and different applications for the vehicle onto the car. You probably never do that for safety critical applications, but there are lots of functionalities in vehicles, and especially vehicles of the future, that offer a lot more functionality. It can be managed in the cloud, but still have a real-time response locally on the vehicle. So this is a very powerful tool to be able to move around your IP and your applications, essentially based on whether you're a premium vehicle or a more of a cost economy vehicle, low cost with less processing capability locally, or whether you have a vehicle that you want to be a delivery van one day, but then it's a personal pickup truck the next day, and you're using the same software and hardware architecture for both of those types of vehicle. Having that flexibility allows you to innovate, allows you to be more responsive to new requirements. And then the other thing that that DDS in particular does is allows you to manage data extremely well. And when I say manage data, I mean different types of data, different priorities of data. So if we think about the in-vehicle domain as an example, there's lots of different sources of data that have different characteristics. Cameras, for example, have a high data volume. They're streaming data at a regular frequency. That data may be if you miss a frame or you miss a few bytes, you don't really need to retransmit it. It's okay to drop some things because you have another frame coming very quickly that you need to keep up with, but also it contains almost the same information as the last frame. That may be very different with LiDAR and radar, where maybe getting objects and you need to know where every object is, and the frequency may be variable. And again, very different from GPS and command and control, or even air conditions, where the data may be much smaller, doesn't have quite the volume that it does in cameras and LiDAR. But it's also very important that you get and acknowledge every command, every control signal, and every error so you can handle that. So the way DDS does this is with a thing called quality of service. And it allows you to tune and change the behavior of data as it's communicated. So you can say, camera data, I want as fast as possible with the lowest latency, but best effort. So if you miss something, I just want to get the next one as quickly as I can. But at the same time, if I miss like 3 in a row, then my application needs to know about it because there's probably something wrong. Whereas with an error code, maybe the latency isn't as important depending on the error codes, but you need to get and acknowledge and log every single error code so that you can understand what's happening within your system. And typically, if we're using a message-centric architecture or architectures used today, you may have 3 or 4 different standards and different ways of communicating that information that needs to be maintained. It's a high expense. Whereas with DDS, you can use QoS to manage the different behaviors, and you're using one set of APIs, one standard, one protocol for managing all that data. It's much more efficient and effective way to develop your systems. And then if we look at how these applications are built, most real-world systems have many different platforms that they need. And if we look at the vehicle, we have different types of ECUs. We have very simple ECUs that don't have a lot of memory, to high performance systems, to network gateways that all need some level of application programming or applications built on them. You have distributed functions, and so you really need to support different hardware architectures from ARM to x86 and x64, different operating systems from RTOS to Windows, and different languages, because your applications really need to be developed in the language that's most appropriate. We wouldn't build a safety critical system with Java, and it'd be foolish to try and build a user interface with C. So the great thing about a data-centric architecture is we're defining data interfaces, and then our APIs can be language specific, and that's how the standard is built, and that's how our solution is built. Is you have many different options for language, from Java to C to C++ to C#, as well as many more that support many different OSs and platforms, really giving you a broad breadth of and depth of options for how you build your system. And all of them access this one shared global data space, which means you're communicating and sharing the same data, and it's still peer-to-peer, no servers and no brokers, which maintains your performance. Now, when we look at ecosystems, Databus can be a common source of truth across multiple different ecosystems, and this is based on work that we've been doing for years with first with the Industrial Internet Consortium, but also with ROS as well as with AUTOSAR, really building DDS into each of these frameworks and demonstrating how you can have a data-centric databus and DDS at the core of your architecture, but then you can be compatible and interface with other DDS-based definitions like the Ruotic operating system, like AUTOSAR, and even bridge to things like CAN bus and simulation and test and validation systems. And we have customers using all of these different technologies and all of these different ecosystems, and really DDS becomes that common source of truth where you can bridge between them, you can share data between them, and you can have this common understanding that really gives you almost the best of both worlds, where you have a data-centric architecture that's very adaptable and flexible, but still access to these very rich ecosystems that are developed with many different types of applications and different IP that you may want to use and reuse in your system. And then finally, when we're considering all of this, safety and security is a very important part of any cyber physical system, and especially an autonomous vehicle. And in embedded systems, security especially, but even safety has not always been the highest priority, depending on the environment that you're working in. But with autonomous flying systems, with more autonomous medical robotic systems, with autonomous vehicles, safety is a primary consideration. But it's not always easy to implement that safety. So as we build these applications, safety is a very important part, along with security, to ensure that you can design and build safety and security right from the beginning. And one of the key benefits of a data-centric architecture building safety is you can really isolate your different systems, which is an important concept when you're looking at safety within automotive, whether it's building to the highest safety level, ISO 26262 ASIL D, or mixing those applications with something different that's maybe at a more of a quality management level or an ASIL B level. By having a data-centric system, you can actually isolate those systems. They really have no dependencies on each other, dependent on the infrastructure, and it's that in combination with something like a hypervisor. It means you can build these very complex but also safe and secure systems. So last couple slides, I just want to show you how, just a high-level architecture of how our customers are building their applications and what they're focusing on. Nothing too detailed, but we start with wanting to build autonomous vehicles, and that's usually where our conversations start. And the most critical, or usually what's considered the hardest part of that, is building the perception and planning. How do I have the right latency and the right throughput? And how do I ensure I can bring in my sensor fusion application that I may have got from one team or one vendor, along with path planning that may come from a different development team or a different vendor. And really, they're trying to build this framework that connects all of these systems together, but also can evolve and adapt as they add more cameras or more LiDAR, or maybe they remove systems if they determine they're unnecessary. And a data-centric architecture is really built for that, and DDS is truly built for that because of the flexibility that it offers. But then as the market's evolved, many of our customers have really started looking at, okay, well, that's the autonomy piece, but what about the entire vehicle? Because it's not just the high performance compute model, it's not just the self-driving capability that we're changing, it's really the entire architecture. We're moving to these centralized architectures. We're building entirely new architectures for these EV vehicles. We need to integrate some legacy ECUs and AUTOSAR Classic, and we need to have telematics and data recording and connections to the back end at all times. And so they need different domains, they need to layer on more capabilities, and they need access to a lot of data. And then as they advance even further, then now we need teleoperations. We need, at first, it's fleet management. It's first understanding where our vehicles are and what they're doing, but with an eye to providing remote control, remote operating capabilities for these vehicles as they're deployed in level 4 or level 5 configurations onto the road. And then when they look at this entire thing, it's really transportation infrastructure that they're building, or transportation solutions that they're building, that goes right from the cloud through operating centers and public, roadside infrastructure and cellular infrastructure to the vehicle, to both the infotainment system and the control, perception and planning system, even right down to the sensors and the ECUs, that they're rethinking this entire architecture. And a data-centric architecture and DDS allows them to build these solutions really much more simply than they ever could in the past, and then continue to evolve them. And that's one of the key benefits of building this, is it's a foundation for flexibility, where as you evolve your technology, innovate, add more applications, add more complexity to what you're offering, the architectural complexity doesn't need to increase when your functionality increases, and that's a real advantage. And so then finally, just one product plug. So Connect Drive is the product that we have for the automotive industry. It's really taking our years of expertise in autonomy and packaging it up into a solution for automotive. Specifically, that includes things like capabilities for connecting to ECUs, connected to the cloud, supporting AUTOSAR, supporting ROS. And that continues to evolve as we work with some of the leading autonomous vehicle manufacturers out there. So that's it for me. I just want to invite you to stay connected with myself. I also like to point out that at least two of my colleagues are on here, Lisa Ray and Kevin. Sorry, Kevin, I'm going to bastardize your name. McInerney is our local account teams for North Carolina, and they certainly can help you out. So I'd like to open it up to any questions that you have at this point.
Thank you so much, Bob. Any question to
Bob, do you think you can share with us the roadmap or the ConOps? Because you have basically this is for level 4 and 5 autonomy. Is that right?
We're working with lots of customers at different stages. Definitely the objective is level 4 and level 5 autonomy for most of our customers in automotive. That's where they want to get to. But really, when we're working with them, we're not working with them on just those applications, because really to get there, they need a architecture and a system within the car that's going to support that, as well as all of the other software capabilities. So for example, as you can see from the EV startups and the announcements that they make, they want a car that's at level 2, maybe level 3, and they want to launch with a vehicle that has that capability. But that down the road, just as Tesla is doing, they're going to add more and more functionality and get to autonomy. So you want to get to that higher level of autonomy, but you may start at a level 2 and continue to build on it. But to do that, you need an architecture, you need infrastructure that allows you to get from a lower level to a higher level, and that's one of the things that we offer. But certainly most of the research and early prototyping that we do with our customers is based around achieving at least a level 4 autonomy capability.
I see. Thank you.
I do have one question. Do you think that ROS is this question might be silly, but here is what I was thinking. Do you think that ROS is a DDS structure by nature, or is moving to that direction? And then if so, then do you think still we need ROS and a DDS sort of middle architecture between ROS and some other applications that we are developing?
That's a great question, and I can give you an opinion, but I don't know that anybody can predict the future on that. If you look at what ROS does, what the middleware level of ROS does, it's a very thin layer that really reduces all the DDS implementations or what other implementations to a lowest common denominator of sorts, but also packages it in a way that makes it easier to use. It's sort of, we're going to predefine the data model for you. We're going to give you certain profiles for QoS that you can use. We're going to essentially limit the different features available from DDS so that you have a simpler time using it, and we have this sort of common way. So if what we say to our customers, if it's important for you to be part of the ROS ecosystem, then use the ROS APIs. I mean, if you're drawing lots of different capabilities from those APIs, use those ROS APIs. But if you're building a production hardened system where you're building most of the software yourself, then we strongly encourage them to use DDS APIs directly, partially because we can fully support those. Like we're not a ROS company, we're just support the ROS community. We can't necessarily support the ROS APIs and say we're going to get them safety certified. That's not going to happen, and you don't have all the capability exposed there. So I I don't ever think it's going to be a black and white, one's better than the other. It depends on your objective. But I can say that our APIs, and we've been doing this for 20 years using DDS, and all of our experience is built in the application, whereas ROS is fairly new, and I think there's still a long way to go to get to that more robust hardened state.
Great, thank you. So any other questions?
Yeah, can I ask a question?
Sure, go ahead.
Yeah, I really loved the one of the opening slides that you have, comparing 1900 and 1913, I believe, how the whole situation got reversed between the. Yes, thank you. And it might be a little bit off the topic from what you presented today, but when you think about the British law of red flag law, I'm not sure whether you're familiar with that. And because of that, whole automobile industry kind of migrated to Germans who has no restrictions and all that. So they were able to build much better technology and things of that nature. So what's your insight on how the policies and the government policies or even state policies have impact on our industry, such as level 4 or 5, autonomous driving?
Well, I think I'm certainly not an expert, but I think if we look at where investments are being made, I think it's clear that the policies of the government, whether it's local or federal or state, have a big impact. I mean, there's a reason that even the Chinese startups trying to build autonomy have offices in the U.S. Because they can test easier here than they can in the U.S., as well as access to talent. Certainly, that's part of it. Mm-hmm. I mean, there's a reason that certain states and cities are selected to do some of the early testing and deployments, is because it's an easier regulatory environment to do that testing. And I'm sure that's going to, as these things get deployed, I'm sure the states and countries that can support more rapid innovation on infrastructure and laws to allow these vehicles on the roads will also see higher adoption earlier. I mean, and then you can look at Singapore, where they actively invest in smart cities and things like that. So that's going to make a huge difference for them down the road in terms of what capabilities they're going to have.
Okay. Yeah. Thank you.
So maybe one more question I do have, and it's about the security aspects of DDS architecture. So I'm not, again, expert in security aspects, but it's kind of my intuition says that, and I think this is a kind of fact that the more distributed you are, the more exposure you have, and the less secure you are, right? So as far as the security, so DDS architecture, the way that you present it, so of course is providing more flexibility and ease of implementation, development, and prototyping, but at the same time, it may raise concerns on the security aspects, because simply it is more exposure you're gonna be having. Isolation is one of the approaches that you mentioned that would be somehow addressing this problem, but I want to see how, and I think this is broadly discussed now, how ROS is secure, how DDS is secure, and how those sort of things, especially moving toward the platforms integration with cloud-based implementations and those type of things, using the DDS architectures and like that. So security questions has been always a sort of concern here. Can you comment on that one a little bit further?
Yeah, that's a great question. I feel like that was a planted question. So we didn't talk much about security, and you're absolutely right. If you don't have a good security architecture, you are creating more exposure. And if you think about the automotive vehicle, we can see the consequences of that. If you've got multiple network access points, from physical to Wi-Fi to Bluetooth, like all kinds of ways you can access the vehicle, as well as hundreds of vendors providing solutions into that vehicle. And how do you manage those vendors, whether it's malicious or just a bug that goes undetected that causes behavior you didn't want. That's also part of your security design. Make sure that, you know, that door module doesn't have access to any data that has to do with steering. If you have these centralized architectures as well as these distributed applications, that becomes very hard to manage. So a lot of security today is based on securing the network level, which really means once you're inside and once you have access, everybody can access everything within that network. It's more like a firewall security, but unless you manage individual access points through a central broker, you can't really say you don't have access to this data or you do have access to this data. So with DDS, there's actually a newer part of the standard. It's a few years old, but called DDS. DDS Security, and our product is called DDS Secure. Just trying to figure out which is which. And this new standard is data level security for distributed DDS-based systems. So it doesn't rely on the network at all. It's actually, if you look at this this layer here where you have the application, this isn't exactly a stack, but if you think of it as a stack, your application passes the data into the infrastructure. It does all these things. One of the other things it does is it can apply security policies to it and then pass it out onto the network. So it doesn't matter whether it's shared memory or a local network or a WAN or over the cloud, the security model is the same every single time. And with this DDS security model, you have a zero trust where you can't access the data if you don't have permission to it. So you can say who accesses the data, what parts of the data they can access, who can read the data, who gets the permission to write the data, and it's independent of your network entirely. So this now becomes a very powerful tool for security within these distributed and cyber physical systems. And it's still, I can't say it's entirely brokerless because you have to manage things like certificates and things somewhere, and that's usually done centrally. But the actual communication is still decentralized, where we actually probably the only protocol that can do one publisher to many subscribers with only one encryption and one security point. So it can be very efficient. Instead of having to encrypt it for every different subscriber, you encrypt it once and can still publish to many recipients. There's a whole lecture that we can do just on security, although I'm not the expert on that. We'd have to get someone else.